here. With little bit of logic. Now, if you have a memory, then in a memory you have an array of storage elements, and you have some logic. You have some decoding mechanism here, and you have maybe some selection mechanism here, but we are going to skip the details. Finite state machines. Like the diagram we had here, some combinational logic and a few flip-flops there. So this, for example, would be your control part of a processor. We can regard that to be a finite state machine. Now, whenever you have a digital functional block, you can describe them in terms of their functionality. And when you design a large circuit like a processor, you want some appropriate performance. So you will design it for performance. So you want to get a high performance processor. And you want reliability. So you want, when you produce a chip, you want to make sure that the chip is produced correctly without any defects, which is actually fairly challenging because everything is so small that it is very hard to make them defect free. So in a batch, when they are making chips, it is likely that a significant fraction of all chips are going to turn out to be bad with some defects. And also a chip can go bad after a while. It has been plugged in, and maybe after a while it sort of randomly develops a defect. How many of you had this happen to you? Did you ever have to, did you encounter any bad memory chips or bad chips in your PC? Or maybe you usually throw away your PC after 2-3 years. So I guess some of you had the bad chips. Solid state devices are fairly reliable. So they tend to be quite reliable. Usually things with moving components, they tend to be less reliable. So for example, your hard disk. Now these days technology changes so fast that some people in some organizations, they recommend that a PC should be replaced every, it depends on how much money they have, every 4 years, 5 years, 3 years. And even ordinary people, any of you have a PC which is more than 5 years old? I still have one. So I have a PC that is, I'm hoping that it's going to become a collectible item. So it's one of the early so-called portable computers. It wouldn't be called portable today, but okay. Now, later on we are going to talk about testing, and we are going to look at exercising a block. So to test, you need to exercise a block. Now, if it is a combinational circuit, you are going to apply test vectors. So we are going to call them test vectors or test patterns. An exact order does not matter because there is no state. Now, if it is a sequential circuit, then you need to apply a test sequence. So if you change the order of inputs for a sequential circuit, your output is going to behave differently, because the behavior basically depends on the sequence, and this includes proper initialization. There is a rather interesting theoretical problem that you will find in some books and also some papers, that you have a finite state machine and you don't know what state it is in, so you keep on applying some inputs and keep observing the outputs, and until you have observed enough to conclude what state it is in at a given time. But in practice that is never necessary, because you always have some kind of initialization mechanism, and that makes the behavior of a sequential circuit much more predictable. And that brings us to our next topic. Incidentally, we are going to be using Carnot maps in our discussion. So those of you who are electrical engineers, ECs, so you remember Carnot maps. So how long ago you used Carnot maps?
I think it's about 3 years back.
Okay, how about you?
A couple of years.
Okay.
2 years.
But it's a rather simple concept. So you haven't used, you have, so go ahead and take a look at Carnot maps, and we have something, I think we have a link. So, and straightforward. The reason I like Carnot maps is that it gives you a visual representation. And I happen to be more visual. Some people are more algebraic. They like to do algebra, and I like to see things more visually. So I use Carnot maps frequently. So let us then go to fault modeling. And that will be our introduction to the field of testing. To achieve high reliability, as I was mentioning, there are two approaches. One is the fault-tolerant approach. You have faults, but you do something so that you can tolerate their presence. And the other is the fault-intolerant approach, which is testing. So you test it as thoroughly as you can. Actually, later we are going to talk about thoroughness of testing, which is actually an important challenge. Now, if you think about the kinds of faults that are possible in a circuit, in a piece of hardware, and that actually is also true for the software. If you think about all the possible things that can happen, you will find that the number of possible faults is enormous. You can have a number of different types of faults, and if you are going to test for every single possible failure mechanism, if you are going to consider each of them separately, it is going to make testing an enormous challenge. And that means you need to do something in order to make the problem more manageable. And that is done by using fault modeling. So basically, a fault model presumes that most defects can be described as well-defined faults. And that is basically a fault model. Now remember, I was referring to stuck at 0 and stuck at 1 fault models. So we are going to look at some of the important things in fault modeling. So we are going to look at the famous stuck at 0 and stuck at 1 fault model. That has been around for quite a while, since I would guess late 60s or something. And I will point out that this is a classical model. This classical model has many shortcomings. It does not represent many of the failure mechanisms that can be encountered. Still, it does a fairly decent job. And it is still widely used. And I'm going to mention about the single fault assumption. So we are going to assume that there is only a single fault present at a time. So do you think that sounds like a reasonable assumption? No. So that obviously is not a reasonable assumption in realistically, except in some situations. Okay, so sometimes you make an assumption in order to make your life easy. So sometimes you will make an assumption, even though you know it is not valid, but it will be appropriate for the specific task you have at hand. Because if you don't make the assumption, you cannot move forward. And so, questionable assumption, but we will see in what situations it possibly would work. So I will mention about the single fault assumption. Now, single fault assumption, I can mention that here. It works well if you are looking at the fault detection problem. If you want to ask the question, is the fault present or not? Is a fault present or not? If you are looking at the question of which particular fault it is, then a single fault assumption will not work. And then we will talk about other faults, other models. And for example, I will mention about bridging, which includes shorts. I will mention about delay faults. And I will mention about switch level faults. Okay, so let's take a look at fault modeling. So how do you know a fault model is a good fault model? So a fault model is a set of presumed faults Incidentally, here we are talking about hardware, but later on I will mention about software testing. In software, there is no such thing as fault modeling. Is that correct? Would you agree? Is there any such thing as fault modeling in software?